Welcome to This Explainer. Today, we're unpacking an everyday mechanical marvel that you probably use without a second thought, the modern elevator. We are going to bring this hidden world to life with some fantastic animated visual breakdowns to show you exactly how these incredible machines operate. We're literally going to strip away the walls and reveal the brilliant physics.
Assalamu alaikum, meet Ismail, an absolute technology genius.
He'll take you from basic electrical theory straight into real, hands-on builds.
Hit subscribe for weekly explainers and let's start building today.
And technology that whisks us up to the clouds every single day.
You know, staring straight down a massive, dizzying elevator shaft like this instantly triggers that primal feeling right in the pit of your stomach, doesn't it? Every time we step into a high-rise lift, we are essentially stepping into a metal box suspended hundreds of feet in the air, just dangling over a terrifying vertical drop. Honestly, it goes against all our natural survival instincts to trust it.
So that brings us to the ultimate question. Have you ever wondered what is actually holding you up? When those heavy metal doors slide shut and the box starts to move, what exactly is keeping you perfectly safe midair? Well, the answer lies in a hidden masterpiece of engineering that has literally changed how we build our worlds. Let's get right into Section 1, the magic of moving up. Okay, let's dive into this, because the basic physics of vertical transit are surprisingly simple but absolutely ingenious. You might think a massive motor just brute forces that heavy cabin straight up the shaft. Actually, scratch that. It's more like a giant playground seesaw or a balance scale. On one side, you have the cabin you're standing in, and on the exact opposite side, there's a heavy iron counterweight. They are perfectly connected by thick steel ropes looping over a wheel at the very top. Just check out that massive sheave, which is basically a motorized pulley, and all those thick steel hoist ropes up in the machine room. Because that counterweight almost perfectly balances out the loaded passenger cabin, the motor isn't actually lifting the whole weight of the elevator and everyone inside it. It really only has to manage the slight difference in weight between the two sides. It's a brilliant setup that means elevators can lift huge, heavy loads using a shockingly minimal amount of power. But you might be wondering, why doesn't it jerk you around when it starts and stops? That smooth gliding sensation is thanks to something called a variable frequency drive, or VFD. Think of the VFD as a really, really good chauffeur. It acts like a mini computer that gradually ramps up the motor's speed when you start and gently dials it down when you arrive at your floor. No sudden acceleration, no slamming on the brakes. When you press a floor button, this controller instantly calculates your position, the weight load, and the direction to give you a seamlessly perfect ride. Moving right along to Section 2, what if you fall? All right, we have to talk about the universal anxiety we all share. What exactly happens if that massive steel rope suddenly snaps? Well, you can take a deep breath because safety engineering has you completely covered. The modern era of safe elevators actually kicked off way back in 1852 when an engineer named Elisha Otis demonstrated the very first safety brake. In this incredibly dramatic public display, he stood on a suspended platform high in the air and ordered the rope to be cut. The crowd gasped, but no way, he didn't fall. The brakes caught him. That single moment revolutionized vertical travel forever. Today, we've built on that with extreme redundancy. Modern elevators use multiple separate steel ropes. If one somehow snaps, the remaining ropes are engineered to be more than strong enough to hold a fully loaded cabin entirely on their own. But the absolute ultimate safety net is the mechanical overspeed governor. This heavy-duty piece of machinery acts completely independently of the motors and electronics. It is constantly monitoring how fast the cabin is descending. If it senses that the elevator is moving even a fraction too fast, which is a sign of a potential freefall, this governor physically trips. Using raw mechanical force, it aggressively engages safety wedge brakes that violently grip the metal guide rails lining the shaft, bringing the entire cabin to an immediate dead stop. Literally every single rope could vanish, and this mechanical beast would still catch you midair. Now let's look at Section 3, sensors and door science. We've talked a lot about the towering hoistway and the heavy mechanics holding you up. But let's shift our focus to the doors for a second. You might not realize it, but elevator doors are an entirely separate, fascinating science of their own. First off, the door you see in the hallway and the door on the actual elevator cabin are two completely separate things. The hallway door physically cannot unlock or open until the cabin aligns perfectly with it on that specific floor. This ensures absolutely no one can ever accidentally walk into an empty shaft. And watch what happens if you stick your hand out to catch a closing door. An invisible grid of infrared safety lasers, known as a light curtain, instantly detects the obstruction and commands the motors to reopen the doors immediately. They are constantly looking out for you. So what about power outages? Getting trapped in a pitch-black metal box is a classic phobia, but follow this sequence for the Automatic Rescue Device, or ARD. If the main city power goes out, the smart controller instantly detects the loss of voltage. Immediately, a dedicated onboard battery backup kicks in. It takes over the vital systems just long enough to safely lower the cabin to the absolute nearest floor. Finally, it provides just enough power to slide the doors wide open, allowing you to simply walk out into the hallway. So even in a total sudden blackout, you are not going to be trapped between floors.
Let's switch gears for Section 4, hydraulic versus traction.
Now that we understand how the safety systems work, let's look at how the architecture of a building totally dictates the type of elevator used inside it. There are two vastly different types of systems operating all around us. Let's break down the two main contenders. On one side, hydraulic elevators. These are wild because they don't use hoist ropes at all. Instead, a powerful piston literally pushes the cabin up from underground. They are incredibly robust and have a simpler design, making them perfect for low-rise buildings, usually up to about 5 or 6 floors. On the other side, we have traction elevators. These use the electric motors, steel cables, and counterweights we talked about earlier. Pulling from above using counterbalance is vastly faster and much more energy efficient, making traction systems an absolute requirement for mid-rise buildings and towering skyscrapers.
Let's put these machine rooms side by side so you can really grasp the visual difference. The hydraulic system relies on a massive pressurized steel tank and a heavy-duty pump. To go up, the pump literally forces hydraulic oil into a cylinder to raise that massive piston. To go down, it simply opens a valve and releases the fluid pressure, just letting gravity do the work. It's pure brute force fluid dynamics. Contrasting that is the traction machine room, characterized by that huge sheave, the large electric traction motor, and all those complex steel ropes. It's a true study in mechanical leverage and precise electrical engineering. And finally, Section 5, the future of elevators. Let's step out of the traditional mechanical rooms and look ahead to the cutting-edge era of Elevator 2.0. Notice how AI is completely transforming the morning office commute in smart transit lobbies. Utilizing a destination control system, instead of mindlessly pressing an up button and crowding into whichever car happens to arrive first, you input your exact destination floor on a touchscreen kiosk right in the lobby. The building's AI calculates the fastest routing for everyone waiting and mathematically assigns you to a specific cabin, grouping you with people going to the exact same floors. This completely eliminates stopping at every single level and dramatically slashes wait times. It's a real game changer. But the upgrades go way beyond just saving you time in the lobby. Modern elevators are becoming highly sustainable and incredibly intelligent. New regenerative drives actually act like miniature power plants. Think about it. When a heavy elevator descends, gravity does most of the heavy lifting. The braking motor captures that resulting kinetic energy and feeds electricity straight back into the building's power grid. We're also seeing machine roomless designs that shrink the motors down so incredibly small they fit entirely inside the elevator shaft itself, saving massive amounts of expensive architectural space. Plus, smart IoT sensors now monitor every tiny vibration and temperature change, predicting exactly when a part needs maintenance before it ever actually breaks. Just look at this stunning cutaway blueprint. It really brings everything we've talked about together. Next time those doors close, I want you to visualize this entire complex ecosystem working in perfect harmony all around you. Thick steel ropes, massive iron counterweights, ultra-precise electric variable frequency drives, relentless mechanical governors, instant infrared safety sensors, and AI-driven smart controllers. They all unite to form what is, without a doubt, an absolute masterpiece of modern engineering. Which leads us to a final, profound thought to leave you with. How will this hidden masterpiece of engineering change the towering skylines of tomorrow? The elevator didn't just make climbing stairs easier for us. It permanently changed our species' relationship with heights, allowing us to build vertical cities right into the clouds. As we push our mega skyscrapers higher and our internal technology gets smarter, the only question left is, how much further up will they take us? Thanks for joining me on this explainer. Always keep your eyes on the skyline and stay curious.